Okay, let's get started. This stuff is already on the board, so that's good. I can reuse it. I want to make sure I repeat the announcement. Very important announcement. The midterm is Tuesday, March 21st, 7 to 9 p.m. So that's the room that we got for everybody that fits. So the goal today is to try to catch up some more, to talk about initializations and optimizers, and then to move into a little bit of a high-level survey of the actual neural net things we're going to talk about in the class. I want to talk about this first. Remember, our goal in working with deep neural nets is to achieve a certain performance. We want to do well on a certain task. We want to learn certain kinds of patterns from data. To learn those patterns, we have to have the combination of, so we need to design, in a sense, a triple, right? We have to have a network / circuit that we have has tunable parameters that we're going to hopefully be able to encode the pattern into. That it'll be able to take data and encode the pattern into this neural network so that it can generalize. But in addition, because we have to use an optimizer, we do some optimizer. Design / choose. Some optimizer that's going to actually be able to take the data and tune the different parameters so that you get a good fit. Why do we do this? It's because fitting is what we know how to do. But you have to be able to start your optimizer somewhere, so you need to have initialization. So the combination of these three, you hope will work well. So you want the combination of these three to bring the right kinds of patterns into focus, is the way I described it last time. So it's not enough for the neural network or the circuit to be able, in principle, to express the pattern. That doesn't do you what you need. That's a necessary condition, right? If you can't possibly express the pattern at the fidelity you need, well, then it's hopeless. But it's not a sufficient condition, because the actual initialization and actual optimizer, when faced with the data, has to actually be able to do it. So I will augment this a little bit to say optimizer, right, and training strategy. We'll talk a little bit about some stuff with the training strategy later. Right, this is like the big picture, what you have. Just a preview of stuff that's going to come later is sometimes our training strategy could involve doing things differently. We already know it has some things, like choosing the loss function, for example. But it also includes things like doing data augmentations during training. It also includes things like having parts of your network that exist only during training, that don't exist when you're actually going to use it. They're just scaffolding to help you build. So think about a building, right? A building isn't put up. There's lots of construction going around in Berkeley. A building isn't just put up just by itself, right? You also have stuff around the building, scaffolding, that helps you build the building. So the same thing exists in neural nets. We'll talk more about that later. But big picture is this is the stuff you have to do. We talked about it before, so it's already on the board, that what we understand is simple linear models. And now we have a way of thinking about nonlinear deep models by view of a local linearization. So at the last lecture, we talked about how basically you can view the model as having, for the purposes of optimization, that it has this local view of what the features are, and it's acting like a generalized linear model in terms of where the optimizer will be focusing its efforts, you can say, for the next part. So, and for simple linear models, we use things like least squares. And again, a part of the training strategy aspect of running the optimizer is what we talked about last time about early stopping. That we can run for free. We can run the optimizer and take checkpoints as we go of the network that's learned. And then at the end, instead of just choosing where we converge to at the end, we could choose any of the checkpoints we saved. And that can often be useful because we said last time that what's happening is fundamentally, when you think about how gradient descent, at least, fits models, is it fits the largest singular values vectors first, then the next ones, and the next ones, and the next ones. And so implicitly, it's going through a sequence of more and more complex models. That's fundamental to how gradient descent itself works. So because of that, you get to, just by running the optimizer and taking checkpoints, you get a kind of view at many different models instead of just one, train one, and you can pick it. The advantage of this, why I said for free, is that if you think about instead using something like a ridge parameter or some explicit dimensionality reduction, that would involve a hyperparameter search. You have to retrain the network using different values of this hyperparameter. And that costs a lot of wall clock time. So whereas this approach of early stopping just uses one run and different checkpoints. So this is the stuff we talked about last time. So now, what I want to do is I want to start thinking about initialization. So for initialization, I'm going to start with the model we had last time that we talked about the simple one-dimensional ReLU model. Let's draw it here. So what are things you might want to do for initialization? How do we think about it? So consider an example. For motivation. So the ReLU example we had was very simple. It was, you take a scalar input, you multiply it by a weight, you add to it a bias, you put that into a ReLU unit, which is max, 0, what comes in, and this is a nonlinearity, and then you took at the output. And we saw before that this thing, as a function of x, if I think of this as y, it behaves like this. Either you have a corner like this, or, sorry, it's a straight line, or you have a corner like this. And in either case, the location of this corner is minus b over w. Okay? So that's where the essence of the nonlinearity exists for this particular little setup. So, notice on this side it's looking linear, on this side it's looking linear. That's where you kind of feel the effect of the nonlinearity. And we mentioned before, you need this nonlinearity to be able to gain the expressive power to express interesting things. Without it, you just have linear functions only. So to understand initializations, let's first understand what would happen if we initialize this weight and this bias to just be normal 0, 1. Just for insight. Set them independently. So if you do this, the interesting thing to look at is, where is this corner? Right? Does everyone see that? Because that initialization, the corner, you ran these, you played with it in the homework, you've seen what happens, you have these little, corners, and then, like this side changes during training and the corner moves around, but, the initial placement of the corners is kind of interesting to know. right? So how is minus b over w distributed? And we won't do the math to calculate this distribution. It's a standard distribution. So this turns out Cauchy. So the PDF, I'll just write it here, of this corner turns out to be, so, where's the placement of this corner? Let's call it C, pi 1 plus C squared. What does that look like? Well, it's peaked at 0, and it goes down like that. So this particular PDF tells us where that corner randomly is going to get thrown down and where it's going to show up. So it's useful and interesting to think about, well, like let's recall some properties of the Cauchy distribution that might be interesting. So you look at the Cauchy distribution and you say, well, what's the property? So you see what it looks like. It's definitely symmetric, about 0. So you could ask, what's the mean? Right? And it turns out the expectation of this thing's mean is undefined. Right? So the question is actually, undefined. Doesn't converge. So if you've never done this, as a side exercise, I would recommend that you take something like the Cauchy and simulate it and track the running mean. Right? Just like, you might say, what does it mean for the expectation to be undefined? If in case you've never seen this before, like, what does that mean? I take this is a distribution. It generates numbers that are between, minus infinity and plus infinity. It's never actually infinity. So I can always take the average of, 100 of them, or 1,000 of them, or 10,000 of them. Like the computation of these averages will always exist. So what does it mean for the expectation to be undefined? Well, you should see it for yourself. I think Wikipedia article on Cauchy actually has an animation of this, but if you haven't done it, you might want to do it yourself just to believe it. Yeah.
But the probability we're very close to 0 is the highest for the Cauchy distribution.
Yeah, so we'll talk about that. So the probability is that this thing is going to be somewhere near 0, but if you compute the expectation, you won't get anything. And the reason you won't get anything is you'll end up having to do an integral that looks like this. Right? You take an expectation like that. Now, if you look at this integral and you looked at it for like 1 of the halves, you might look at this integral and say, wait, actually, I know how to do this integral. Right? You can do this integral in closed form. Right? I'll leave that to you. But if you look at this, what you'll see is that asymptotically, the denominator behaves like c squared. Right? And the numerator behaves like c. So asymptotically, when the values are big, this thing is behaving like 1 over c. But 1 over c, the integral diverges. So the integral diverges on both sides. So this thing tends to infinity slowly, but it does tend to infinity. Okay, so this thing doesn't have a mean, which means that it's heavy-tailed. Right? You can see it's a polynomial tail. So it's heavy-tailed, so in this case it doesn't even have a mean. So it definitely doesn't have a variance. Right? It doesn't have any moments higher than or equal to 1. So you can still ask, well, sure, it's still a distribution though, so it still puts its probability mass somewhere. Right? It still has a CDF and everything. So it turns out, for looking at this, that if you go out, I just picked a couple of numbers at random, to minus 10 and plus 10, in between that, right, this contains at least 94% of the corners. Right? So although this thing has a diverging expectation, it still means that actually the action, the corners is going to be between minus 10 to 10. You could pull in much closer, right, and look at minus 3 to 3. Oops. Just as a way to get some intuition. And between minus 3 and 3, this has 80%. Does everyone understand what I'm doing? Right? We want to look at where these nonlinearities are. So this actually instantly tells you some concepts that we'll also that will come up in deep learning. That's good to know. So first is, hey, actually, whenever you have a ReLU network that has ReLUs in it, and you have random initialization, it could be that all of your data that you have is all living like here, right? Like your data is whatever it is, and we'll talk about this in a moment. But your data is wherever it is, and that means that some of the ReLUs will be like have a corner that's out here, so they'll be like at initialization. Do you see that? Right, because it's random, right, where these things fall, and you have tens of thousands of them or more. 94%, fine, 94%, but 6% is still 6% of it's thousands of units, right? They're looking like this. So during gradient descent and during stochastic gradient descent, they always just give 0. Does everyone see that? So these are what are called dead ReLUs. Right? So when that happens, they're called dead. So it could be like this, or it could also be the other side. So a ReLU that on training data always shows up as 0 is dead. It will have no gradients. It will never undie. So, okay, that happens for ReLU networks. But even the ones that are the counterpart of this, right, that look like they might as well be dead, right? I mean, they're not dead. They'll have a gradient. But to actually have them do anything interesting, you would need to have the corner actually move such that it's actually different that some training points are on different sides of it. But it might never do that. So in that case, this kind of ReLU will just always behave like just some linear thing. But it won't contribute any interesting nonlinearity. And so all the ReLUs that are in that kind of state will be their own different kind of object where there's just a linear thing that's happening. Okay, so these are all things that can happen with ReLUs. Now, one of the, why do we care about this? We care about this because we definitely want it to be the case that from a pragmatic perspective, if you're going to have a local gradient descent type optimizer learn an interesting pattern, that we don't want all of the inputs, all of the training data, to be out here, right? At the past minus 10. Do you see that? Because if you do that, you're going to start with almost everything being dead, or effectively dead. Not interesting patterns. So what you want, a desirable kind of quality, kind of intuitively, is to have the input that's going into one of these units kind of be centered around 0 and have most of its probability kind of in the near neighborhood of 0. Does everyone see that? Ask a question if you don't understand that. Yeah.
So we're using our data, so we're kind of like
Yeah, so what you want to do is you want to think about your input to, like, so remember, we're trying to understand what's going on in a deep neural net. Right? That's our goal. So in the deep neural net, you have many, many layers. But all the time, you'll have these nonlinearities with stuff like right in front of them, weights and biases in front of them. So we want to make sure that as we're going, that if we need to do a mean shift or something, that at initialization, things should be at a reasonable place. So there's two parts of it. There's what your actual training data is. And we'll talk about the normalization or standardization of your actual training data later. Like, it's fine. Yeah, exactly. So you could, for example, take your actual training data, the things you actually get from, observe from nature or something, and change units so that there's zero mean and, for example, standardize the variance to be 1 across your data. Yes, you could do that. That's a very reasonable thing. But the problem is that in a deep neural net, so I'll just draw a little picture of it. Recall what this class is about. Is you have layers upon layers of stuff. Right? And so even if you have standardized the x coming in, from the perspective of gradient descent and learning, this thing is the input to this guy. And so if you don't initialize properly, right, what will happen is that this is nicely standardized, but then this isn't. Everyone see that? And so the same problem that we talk about will happen not here, but here. Like everything here will be a dead ReLU, or we'll be behaving like a linear thing. In which case, maybe everything past here, all this depth that you were adding to get certain things into focus or to do something interesting, all that depth is just like one big linear layer, effectively, right? If everything is sort of, dying over here. Yeah?
Could we just standardize?
Great question. The question is, can you standardize at every layer? We will be talking about that, and we do things like this as an alternative thing. We'll talk about that when we talk about conv nets, because it's required to make modern conv nets work, is stuff like that. So we will do stuff like that. But another thing we could also do is to say that, like, at initialization, stuff should behave reasonably. That the main work shouldn't be coming from the standardization.
Are those dead ReLUs absolutely bad thing? Because I think they would behave like, drop out.
So the good question. The question is, are the dead ReLUs bad or good? Right? It's always good to ask. If you see a phenomenon, you have to ask, is this thing a good thing or a bad thing? So from the perspective of implementation and, wall clock time and, how many meals you can cook on your server while it's running, the dead ReLUs are a bad thing because their computations are being executed to compute for them. Like a whole bunch of numbers are being multiplied by weights, a bias is being added, and then it's compared to 0, and it always is less than 0. So a whole bunch of compute is wasted. From that perspective, dead ReLUs are typically viewed as being bad things. But you could ask, does the presence of a lot of dead ReLUs act in a good way for your network, like in some regularizing way? And the jury is kind of out on that. In terms of people aren't really sure. They mostly think it doesn't help. Dead ReLUs have another. Since we're talking about dead ReLUs, I'll mention another thing about dead ReLUs is sometimes stochastic gradient descent. So you have this homework problem, right? We worked out how does gradient descent work on this, right? In terms of like moving this corner. But sometimes stochastic gradient descent type algorithms can, because of local randomness in the batch that was selected, could generate a gradient, and if the learning rate is high enough, it could kick the ReLU in such a way that it becomes dead. Okay? Like it's just sitting there, it's in a reasonable place, but some weird thing happens with the batch. This thing gets kicked, especially if you're using an adaptive optimizer, it gets kicked in some way, and bam, now it's dead. Problem is, when that happens, it's going to stay dead. So there is this problem that people have observed in real neural net training when you train for a very, very long time, is that slowly ReLUs will start dying. Right? Just randomly. They'll die, they'll die, more will die, more will die, more will die, more will die. And some of that might be a good thing, like it might be actually removing degrees of freedom you don't need, but people have observed that sometimes performance gets worse because now too many of them have died. And so it's a really good question to think about what happens with dead ReLUs. But yeah, you have to be aware of the phenomena. So notice that I'm talking about the ReLU nonlinearity because it is in some sense the easiest to understand intuitively because it has the nonlinearity constant in one point. But a similar kind of concern of wanting to keep things in some appropriate center applies to all the other nonlinearities too. Right? So if your nonlinearity is something like has a sigmoidal shape, right? Then something that saturates. Then the problem is if you're too far out where it's saturating, you're going to get extremely tiny gradients, and you're basically not going to move. It might as well be dead. Okay? So this kind of concern exists in all nonlinearities that you have, that you work with, that you want to keep things kind of. So we want the action here. And so one of the approaches that we do, if you want to think about some kind of object which, random object, which hangs around 0 and is kind of some reasonable width, our default thing to think about is normal 0, 1. Right? So we think about, hey, maybe we want to have stuff have mean 0 and variance 1. So I want to give myself more space. You all can remember that. I'll just draw the picture again here. Oh, I'll draw it here. Can we keep... At initialization. Now, we don't really care about the fact that it's normal. We just want it to be kind of contained. The only thing we have easy abilities to work with is to think about, scaling and things like that, because we have a network that's built out of, weights and biases. So the picture I'm going to draw. So I'll just repurpose this into a boundary. Remember, we have a deep network. Okay, so I'm going to zoom in, somewhere in this story, like here. So here we have the preceding layer. And the preceding layer has some stuff, okay, followed by some nonlinearity. It could be a ReLU. It could be, something that's sigmoid, tan H, whatever nonlinearity you have. There's something back here. And the output, by convention, the output of the nonlinearity is deemed the output for standard multi-layer perceptrons. You just have a big graph, a big circuit, so you have to decide what's the layer. You say the output of the nonlinearity defines the boundary of the layer. Okay? So this is the output. Output of previous layer. And you have many such things, right? So many such outputs. And then we have the next layer. Okay? This layer. And this layer, we start with a bunch of weights. So I'm going to look at the top one. So this gets multiplied by a particular weight. This also gets multiplied by another weight. And so on. All of them get added up. And to this, a bias is added. Some bias. And then this enters the nonlinearity. Right? That's how those networks are put together. Right? And so on, it repeats for all of the others. Right? So this is the next output of the next layer. Everyone good with the picture? Zooming in. So what I want is I will make the assumption. I'll say, for starting off, I'll make the assumption that suppose the output of the previous layer is the input to the next. Suppose I've already achieved the output of the previous layer is already like normal 0, 1s, a bunch of normal 0, 1s. And I want to make sure that what I actually see in the neighborhood of this nonlinearity is also like normal 0, 1s. Okay? What do I need to do? So I focus on this point. And I say, look, all these weights are going to be multiplying a bunch of numbers that are all kind of in the neighborhood of, 0. In a nice neighborhood of 0, such that their total variance is something that's like, 1. So I want to multiply them by things, add them up, so that I get something which is also in the neighborhood of 0. Right? So what can I do? How can I initialize these weights? So I'm going to make the assumption for initialization that, I'm going to assume that all of these things are, whatever they are, right? These things I'm going to initialize is going to be independent of each other. So I would like to have this thing are all normal 0, 1s. So they all, one way of viewing it is, as a giant vector, this vector has a norm which is about the fan-in, right? So the norm of this vector is roughly the fan-in of this unit. So think about the number of things here. So say there's d of them. D such edges. So from a circus, you've heard the term fan-in? Like the number of things connecting to a gate, right? So there's d things. The norm of this is typically going to be d. And so I want to have these w's be initialized some way, independent, such that the output comes out to look like it's, around 1, at 0, normal 0, 1. So the way to do this, right? So I'll just write it here. It's called Xavier initialization. It says, initialize the weights IID, normal, instead of 0, make them 1 over the fan-in for the variance. If I do this, then when I multiply it by something, right, like I have there, so sorry, I said, if these things were, okay, be more precise. Because these are all normal 0, 1, the norm here of this vector can align to be about d, if everything was actually aligned, right? But if all these things were random, it's actually going to have a norm that's like square root of d. You're adding a bunch of independent things, right? When you add d independent things together, and you look at what happens, you'll get something that's order square root of d, because of the central limit theorem. So if you think that at initialization, all these things are as though they were independent. Now, notice, they're not independent, right? Because you have a single x, whatever it is, going through all these things. There's some dependency structure that's induced by all this. But you want to say it's as though they're independent vis-a-vis at least second-order properties, right, in terms of correlation. And you just hope There's literally a hope. So let's hope that's true. Then I can use this initialization to get the desired effect. Any questions on Xavier initialization? So Xavier initialization will result in the thing that comes in before the bias being roughly, variance 1. Yeah.
What's the point of the variance?
Excellent question. So initially, I said, look, we just have to be in the neighborhood of 0. And I immediately jumped to variance 1. Okay? So the question is, what's so special about 1? Right? Does 1 matter? And here's why 1 matters. 1's a very special number, right? Because there's two numbers such that, in the reals, there's two numbers such that if you multiply by them repeatedly, you will stay in the same place. 1 times 1 times 1 times 1 times 1 is 1, and 0 times 0 times 0 is 0. Everything else, if you do it repeatedly, will either blow up to infinity or decay down to 0. Is that clear to everybody? It's a really great question, like why 1? So we're thinking about a deep network, right? There's many, many layers here. So we're going to do the same thing over and over again. So if we said, you know what, I'm fine with the kind of variance coming out of here being, like 3. And then I'm using some nonlinearity that's not so saturating. But there's an assumption here. It's not so saturating that it'll manage to squash it down. Then I'll get something coming out that's also going to be variance that's, bigger than 1. At that point, what will happen is I'll repeat this process, and it'll get bigger, 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 bigger. And that we don't want. Why don't we want that? We can go all the way back to see the gradients, right? The gradients will be too big. Yeah?
In case of the Xavier initialization, the variance of the output may be less than 1, because there will be some dead value. Right?
Yeah, so it's a great question. So I'm talking about Xavier initialization. Exactly, let's do the next thing, right? Not quite right for ReLUs. Exactly, right? Problem is that if the nonlinearity in the previous layer was a ReLU, then you expect half of these outputs to be 0. By dumb luck, right? The input landed on some side of it, so half of them are 0. So although it looks like you have d of them, you actually only have d over 2, right? So for not quite right for ReLU, and so that's why there's her initialization. So her initialization applies when the output of the previous layer is ReLUs. Like when the previous thing was ReLUs, use her initialization. Her initialization says you don't have d things, you have d over 2 things. So you take the reciprocal of d over 2. Yeah, question.
Is it d for each layer that you're going through, or d like the y-is pointing here?
Ah, yes, so great. This is d, which is fan in per unit. So all the weights are connecting into something. So all the weights look like this, right? So if your layer has an asymmetric fan-in, it's like whatever the fan-in is for this unit, use the d for that. So same thing here. It's the fan-in for the unit. And now what matters here is use when previous layer has ReLU. Yeah.
Explain again why when the previous layers are d over 2.
Ah, so great question. The question is when this previous nonlinearity was a ReLU, the fan-in is still in the graph d. But you expect at initialize, remember, everything you expect is you want the inputs to look like they're, kind of 0 mean and on either side, right? Balanced around 0. So that nonlinearity, that ReLU nonlinearity, looks like this. So you expect, at least at initialization, that whatever that input was to the previous layer, half of the ReLUs are here, and the other half are on this part of the ReLU. So for half the ReLUs, you expect the output at the previous layer to actually be 0. Draw a Gaussian. Draw something from a Gaussian, let's say. And what is the probability that the sign for the ReLU centered at 0? What's the probability the sign is greater than, is positive? 1/2. That. Okay? So if you think, wait, but the ReLUs are at different places. Sure they are. But as many of them that are on this side are on that side. So on balance, you still expect about half of them to be, for that particular input, to be dead. Now they're not actually dead ReLUs. They're just 0 ReLUs for that input. A dead ReLU is 0 for everything. But it still matters, right? Because the next layer actually sees for any particular input something. So you can't have it blowing up for a particular input. Okay, so that's why you do high initialization. Any questions on high initialization? Yeah.
When you say like you mean like on.
So it's a great question. What I meant is that typically we'll have a symmetric fan-in for the entire layer. But you might, just abstractly, it might be that at the next layer, some particular nonlinearities are connected to a bias and a set of weights that touches everything in the previous layer. But some might have weights that only multiply a subset of the previous layer, just because of how it's built, right? So you can't just use the size of the previous layer. You have to look at the fan-in for that unit. Like how many things does it actually have non-zero weights multiplying? That's what's meant. So looking ahead, right? In a standard multi-layer perceptron, a deep neural net, the D will just be the number of outputs in the previous layer. But when we think about convolutional neural nets and the like, then everything won't be connected to everything in the previous layer. And so we'll have to think about what that actual fan-in is for doing the initializations, which is why I'm talking about in terms of fan-in. Yeah? Sorry?
Which is the gain in terms of dead ReLUs when we do something like that?
Great question. The question is, what is the gain in terms of dead ReLUs when we do this? The gain is that if you have ReLUs in the previous layer, then about half of them will be 0. So when you do this, when you make this a little bit bigger, like square root of 2 bigger, effectively, because what happens is the input to before the bias term will actually tend to be something that's like normal 0, 1, as opposed to normal 0, 1/2. And so what will happen is that as you keep going through deeper and deeper, you'll prevent everything dying out to 0. It's trying to fight things just dying out to 0 as you go through on particular instances. Yeah?
If you introduce dropout into your network, how does this play into that? Would you have to change it?
Great question. We'll talk about dropout later. As another as we go through, we'll introduce more and more building blocks as we need them. I want to give you a basic picture first, but yeah. So but I'll answer your question. So dropout is another thing that one does during training. It's a training strategy for some regularization. It's something that operates when you're actually training. What we're talking about here is initialization from scratch. So when you're going to do initialization from scratch, you pretend you're going to use the entire network. It's a good question to ask, which says if you're actually going to be training with dropout, and every time you're going to be running your training, you're going to only have half of your units actually be giving outputs, and the other halves will be set to 0. Then do you need to adjust your initialization? Great question. However, the way we solve that problem is not by adjusting the initialization. We solve that problem by adjusting during training what we do. Okay, so there's something you can do there. Now you could also say, okay, it's a choice of where you put it, right? There's training time, there's initialization time and there's inference time. And so you can think about how you do the adjustments. But yeah, it's a good question, and it's kind of a choice of what you do. Yeah.
I wonder as we have changed the distribution of the parameters and as beginning we have assumed that they are no distribution with variance of one, and we know that it forms of the distribution. So when we change the distribution, do they still follow the standard distribution?
Excellent question. Great question. Question was, okay, we started off by saying we have something that's normal 0, 1, just to tell you why we care about the neighborhood of 0, because we get the Cauchy, right? But now we're talking about initialization to different things. And so we have to say, with these new initializations, do we still care about the neighborhood of 0, right? That's kind of a really good question. So it's good to step back and look at this thing again and ask, hey, why is this thing Cauchy? Now you could grind out integrals, okay, to do it. But that doesn't help you because now you change things. So you need to understand more deeply, spiritually, why is this thing Cauchy, meaning why does it have heavy tails like this, right? Why does it look like this? So the fact that it'll be centered around 0 is coming from the bias term. Does everyone see that? Like clearly, if the bias term is around 0, like this thing will be centered at 0. Everyone good with that? Okay. So that's the bias term. Even if the bias term was somewhere other than 0, the fact that this thing in the denominator is symmetric would also say, who cares about that sign? Right? So the centering at 0 is pretty solid. Did everyone see that? As long as I don't make the bias term like some big number. Right? Good? So the other interesting quality we care about is the fact that this thing is heavy-tailed. Right? That it actually doesn't have a mean. Right? Good. So does that need both of these to be Gaussian? No, it does not. What's making this tail extend? Like what would throw an elbow out far? What would throw an elbow out far is if this weight became small. Right? To move out far, it doesn't matter, like, yeah, sure, the bias could be big, but we already said we don't have that. So it's got to be the case that the W is small. So all that matters to make this thing spirit like a Cauchy is that whatever this distribution is should look flat near 0. You see that? Because if it has a density around 0 that's flat, that'll induce a heavy tail in the ratio. So everything we're doing is still making the distribution flat near 0. And so we still have this qualitative behavior. Okay, great question. And why you have to be able to reason about these things more closely. You start with a simple example that you can kind of analyze, that you can think about and kind of draw results for. But you have to understand why it's actually true from an intuitive point of view. What I'm talking about here is math intuition. Because that helps you deal with, okay, we have changed things. Is it still going to happen? So, yeah, great question. Yeah?
So going off that, if the variance is smaller, does that mean like the tail would be?
Great question. If I made this W have more and more mass near 0, what happens to where the corner goes? When you divide by something that's closer to 0, does it get bigger or smaller? Bigger. So that will throw these things out further, which is bad. Right? It'll make everything dead, which is corresponding to the or linear, right? Everything's going to be dead or linear, which corresponds to the loss of expressive power that we're afraid of at initialization. Good question. I want to be able to talk about optimizers, so unless it's particularly urgent, I want to be able to move to the next thing, okay? So hopefully this gives you a sense for the initialization. So final comment on initialization is, what about biases? So I've told you how to initialize the weights so that things don't blow up and that things stay kind of nice, hopefully, at initialization all the way through. What about the biases? So it turns out for biases, there are many choices of what to do, all of which are tried in the literature. And remember, what's the standard default rule in deep learning? It's look at the papers that you're building on, do exactly what they did, right? So as a starting point. So the same thing applies even for these initializations, right? But what about biases? So it turns out there's like 4 choices that are all used depending on the paper before. So you should just be aware of them. One is treat Fanion as D plus 1 and use Xavier. So just instead of thinking about this sum followed by of all the stuff that's been weighted, followed by a second sum as the bias, think about the bias as connecting to a unit that always says 1 and just being another weight. Does everyone understand that? So this changes the Fanion. Treats like Xavier. Of course, this one will never die, so you can do the appropriate adjustment for H, right? So that's like one approach. Just treat it like everyone else. There's the second one that'll strike you as being weird, but it actually works in many cases, which is just use bias equals 0. Initialize to 0. So you might say, wait, if I initialize to 0, then all the corners will be at 0 to start with. Doesn't that introduce a lot of redundancy? The answer is yes, it does. But remember, everything before is being multiplied by random weights. So the first few steps of stochastic gradient descent will kick that bias somewhere. So let's let SGD initialize the bias for you in the first few steps. Does everyone see the kind of spirit of this? It's like, why should I have to do the work? Let SGD do the work. Related to this is maybe 0 is not so great, so pick a small number. Or some other small number. Again, people have empirically seen that sometimes this does better than just using 0, despite the fact that stochastic gradient descent is still shaking everything at the beginning. And 4 says, what's so special about 0.01 or any other constant? Use a small random number. So people use uniforms and things like this. Again, you look at papers, you'll see what they do. You should follow that for initialization. All this stuff for random initialization is becoming less and less practically relevant today because, as we said before, that in many cases today, when you're using deep networks, you're going to initialize not to something random, but to something that has been trained in some other way. But you still have to initialize that in some random way. So it's still like in the background, you need to know it. OK, good. So now hopefully you understand a bit about how this initialization works in deep networks, what it is that we're trying to do. We're trying to avoid things exploding or decaying away in the network at initialization, which is required to make sure that at initialization, the features that the optimizer sees are interesting, that they don't just have like everything being 0 or everything being 1. I want to comment a little bit about why it's bad if everything gets really big. You can understand why it's bad if everything gets really small, because it just goes to 0. But what's wrong with everything being really big? So what's wrong with everything getting really big is that the gradients will also get really big. And if the gradients get really big, it means that there are certain directions that you're moving in terms of the giant space of weights and biases, which will have enormous singular values in certain directions. It'll be huge singular values. There still might be other directions that have very small singular values, or even moderately reasonable ones. And what will happen is that the giant singular values will force you to use a learning rate in gradient descent that's small to avoid divergence. But having used a small learning rate for those, you're using the same small learning rate for the other directions. And those other directions will basically not be able to move enough during wall clock time. And so you'll just not get to be able to converge to anything interesting if just initialization is causing you to have wildly huge singular values. Yeah.
Let's say if it gets big enough or small enough, would it cause issues such as integer overflow or like floating points being undefined when you're actually doing calculations?
Yeah, great comment. I'll repeat it to make sure it's recorded. I've focused on things as though we were doing arithmetic, all the arithmetic, using perfect real numbers, and just talking about what happens to singular values and the like. In real systems, you're using some kind of floating point representation. And there's increasing call, for reasons of wall clock time and computer architecture, of trying to use smaller floating point representations. And so the danger of overflow and underflow is present. And in fact, yeah, if you have anything which threatens exploding gradients or completely dying gradients, you'll just overflow or underflow your finite precision arithmetic. And then you will get like complete gibberish. And so, yeah, in real life, that's another consideration, which is important. But thankfully, we can talk about this consideration without having to, at this level, we can talk about the issue without having to reference finite precision. Right? We can just think about even if we had perfect precision, real arithmetic. Okay, so this is good. Now what I'm going to do is I'm going to switch to talking about optimizers. And I want to make sure that I at least get to introduce the key ideas behind momentum. Something I didn't erase. Okay, so let's understand the problem first. So for understanding the problem, if you don't understand what I'm saying right now, discussion tomorrow will help you make sure you completely understand what I'm saying right now. Okay, but it's kind of the prereq to everything else. So the problem is, if I look at the singular values, again, we're going to go to the linear model, because that's what we know how to understand. If I look at the singular values, I'm going to count the different singular values, and I look at what they are, right? I might have the first one be big, and then another big one, another big one. This might be on a log scale, right? I have some big ones. And then I have some that are getting small. But it might be that these small ones still represent directions in terms of singular vectors that are actually relevant to the pattern you want to capture. Okay? So your pattern is actually, think about it, is locally, 20-dimensional. And you have these 20 singular values that are all relevant. And then you have a bunch that are much smaller. Okay? Like tiny, tiny ones. What you would like to do is to get good convergence in wall clock time on all of these. So you care about these. These ones down here that are hopefully much smaller represent directions that you don't really care about converging in. In fact, if you did converge in them, maybe you would get, if you were doing ridge regularization, you'd regularize these out, right? But you could do early stopping, and you don't want to necessarily have these guys get too big. Okay? So we have a goal, which is we want to make sure that we can optimize as fast as we can by taking steps on the directions we care about without causing us lots of trouble on the directions we don't care about. Okay? Like a high-level, vague introduction to the problem. But that's really what we face in real life. So, if you're using gradient descent, sigma max is limiting our learning rate. Because if you make the learning rate too big, this will go unstable. Let's think about what happens qualitatively. Here's learning rate. Call it eta using the step size standard notation. And let's think qualitatively what happens. So here's 0. So for the direction associated with sigma max, how does convergence behave? When you're close to 0, it's, slow exponential, which might as well be linear, right? It's too slow. Then you have call it very slow exponential. Then you have slow exponential. Then you have medium / nice exponential. Then you have a magic value, which is instant. Right? There's like for a particular sigma max, there's a particular learning rate such that in one step you'll converge. Right? That's just like a magic value. That's when the eigenvalue goes to 0. Right? So instant convergence. And then you have learning rates that are bigger. And the ones that are bigger are like mirror images of what's happening here, except kind of, so, like unit circle. These ones are slow here. You're moving closer, closer. This is the 0. And then you're going over on this side. So on the other side, you're oscillating, exponential. Nice. And then you're oscillating ominously, but not quite dangerous yet. And then you diverge by oscillation, increasing like bigger and bigger oscillations. So when we say the sigma max is limiting our learning rate, it's limiting, it puts a hard limit here. You can't make the learning rate bigger than this, or you'll oscillate away. But actually, it doesn't particularly like what's happening here either. Okay? So this is something you need to understand. If you don't understand it from the very quick descriptions that we've talked about so far, discussion tomorrow will definitely help you do this, as will the and it's so important. We repeated the question that'll be on discussion tomorrow on the homework. You have to know you have to know this. Anyway, so you have this problem of limiting the learning rate. So what happens is the learning rate exists kind of on sigma max scale. So for the smallest singular value of interest, small but interesting, for that one, so that this is this one, and this is this one. Okay? What does this picture look like? On the same scale, what happens is that everything just kind of expands out, right? into larger windows. So the problem is that what you're really worried about is actually not this case, where in this case, if you take the sigma max and you put it into a nice place, like here, right, that's oscillatory. Down here, this is still, maybe kind of good, slow exponential, right? And you'll still get things to converge. You can increase the learning rate and have things work. The problem is that it could be that this is like even more spread out in terms of where the regions are. And even if you took this sigma max to the kind of nicest place, the limit of oscillation that you can still converge reasonably, you're still super slow on this value. And so you're just going to converge slowly. There's no choice. You balance the two out, and you converge slowly. Does everyone understand this concern with gradient descent? This is like the core issue with gradient descent. Is yes, it has this implicit regularization effect of not favoring directions that are small, but maybe some of those small directions are directions you want to favor. A little bit. But you don't know where they are a priori. So what can you do? How can you make the learning rate bigger? So you want to make it for smaller sigma while avoiding instability in larger ones. So there's all the optimization approaches we have at some high level are trying to attack this problem. Right? Like, what can you do? So, the first approach we're going to talk about is called momentum. And what momentum does is momentum says, hey, I actually have a warning sign in spirit of when I'm making the learning rate too big, which is that I'll see oscillation. Everyone see that? When you make the learning rate big on the large sigma, I'll see oscillation. A particular kind of oscillation. This is discrete time. Remember, the learning algorithms run in discrete time. So it's an oscillation that goes tick, 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 like that. Positive, negative, positive, negative, positive, negative, like that. So you ask, hey, do I know anything that will allow me to suppress oscillations, but not suppress something which is steady? Remember, this side is steady here. The small eigenvalue, the small singular value direction, the gradients are evolving steadily. Right? They're smooth. On the large one, they're becoming oscillatory. So there's a question, right? Momentum says, can I reject oscillations while preserving steady things? And the answer is yes, we know how to do this. We can use a low-pass filter. Idea. Low-pass filter gradients. If I low-pass filtered the gradients, what would happen is that where I get the oscillations, I would get attenuation of the gradient. Right? It would get smaller. Which is exactly what I want. What I want is I want the gradients on this side effectively for the large sigma max to become smaller so that I could use a larger learning rate. Right? So I want to be able to have the oscillation get attenuated while doing nothing to the almost DC looking behavior of the gradients for the small. And so now the question is, you have an idea. How can I low pass filter the gradients? Like, what can I do? So you just think of what's the simplest low pass filter you have, right? What is low pass filtering? It's a kind of averaging, right? So make the simplest averager you can. So average the gradients. Low pass filter just means average. So use the simplest averager you know, which I'll describe. And then I'll show you an analogy for those who can understand it. Okay, so low pass filter. Right. I'm looking for something that looks like this, circuit-wise. Right? Circuit analogy. This will low pass filter voltages. Right? If something is steady, the capacitor will charge to that level, stay there, and it'll steadily go through. But if this is oscillating, you'll be pushing charge in and out of this capacitor, this will stay small on the outside. Right? So I want this. So the nice thing is this has a first order differential equation. And it corresponds to the following approach to averaging. Right? So I can make the following averager. This is internal, this is state. Okay. So discrete time. If I want to average numbers, I can say the average at time t plus 1 is 1 minus beta times the average at time t plus beta times the thing you're averaging. So this is a time sequence. Okay. Beta is some number, which is in 0, 1. Okay, so first, even if you don't remember this, that this is the first order differential equation, has low pass filter behavior, if you look at the discrete time formula, you should see how this is a kind of lazy averaging. It says, how do I average? I maintain an average, and I multiply it by something that's pretty close to 1. And then I multiply the new thing by something that's small. And by doing this, I'm effectively averaging that sequence out. Do you see that? Because if this is a constant coming in, this will just be the same constant. But if this thing is attempting to bounce back and forth, right, this will be a much smaller, more steady thing. Right? Because this thing's attempt to bounce up and down will be a small fluctuation on top of this. And so it'll get dampened down a lot. So this is actually a classic trick that we use all the time. Whenever you have the intuition of wanting to do an average, and you want to make it implementable in a way that you could analyze as well as make it easier to implement, averages naively implemented are really annoying. Because if you want to take a moving average of 10 things, you have to store 10 things in memory and take their average. But this requires you to only have one internal state that you keep track of. And it basically does the same kind of averaging that you can adjust how long you average by choosing beta. Sometimes called exponentially smoothing things out, but this is a really useful trick. And it's basically coming from this analogy of the behavior of this thing. So what you do is gradient descent says I take my parameters, theta, t plus 1, and I set them as theta t plus an eta times a negative gradient of something, right? The function you care about. And so this has a t in here. Right? So what you want to do is gradient descent with momentum. The goal is I want to replace this object with instead a smoothed version of the gradient, a low-pass filtered version of the gradient. So I can do that. So I say instead, okay, and did everyone see what we did? It's like just like gradient descent, except instead of using the gradient, you use this smooth gradient, which has been low-pass filtered. Okay, I'll pause here and take questions to make sure that people understand. Yeah.
So if that direction is figure out not oscillating, but that like low pass filtering would also behave like that you desire.
Yeah, so exactly. The question is if this u, right, the input to this little box, right, is constant, is steady, or is moving gently, which is what would happen to the small the derivative in the direction of small singular values, because you haven't moved that much, right? It's very steady. That will just pass through here happily and will not be attenuated at all. So all of these guys don't get any attenuation, while this guy gets a lot of attenuation. What that means is that you can jack up the learning rate. Yeah. Great question. The question is, will this prevent divergence for the sigma max? And the answer is no, but it will hold it off for a larger learning rate, right? It'll still diverge. But the thing is that, okay, so this is so important. You have an entire homework problem dedicated to analyzing what's going on here. But let me tell you like some higher level pictures of what's going to happen. High level picture of what's going to happen is singular value by singular value, you instead of having one state only, which is theta, in that singular value direction, you'll also have the component of A that's in that same direction. Okay? For a linear problem. So what you have, instead of when you finally look at it, instead of having a recurrence relation in a scalar, you'll have a 2 by 2 recurrence. Right? Because you'll have two state variables. The actual parameter and this kind of smoothed velocity. How can 2 by 2 matrices evolve? We'll get complex eigenvalues and complex eigenvectors. And so when they diverge, they will diverge by oscillation, by spiraling out. Okay, so you can still get divergence, except instead of being kind of bang, bang oscillation, it'll be like a spiral that spins out of control. And so momentum approaches, they're called momentum. If I had my way, I would call it just gradient descent with smoothed gradients, because that's more what you're trying to do. It's called momentum because what you effectively have is the old gradients that happened are still affecting how you move through this. So that's the idea. That's why I got the name momentum. Now, a warning. I have drawn it for you and described it in the context of a parametrization that is the most natural to understand what is going on, right? Because you have 1 minus beta beta and eta kind of separated out in some nice way. If you look at PyTorch's documentation, in PyTorch's documentation, the PyTorch parameters that control the level of momentum are not cleanly separated this way. So here, I've chosen learning rate to mean the same thing it meant before. But in PyTorch, learning rate in the context of calling it momentum means something different. This is confusing, yes, but so what? So well. Nothing you can do. That's life. That's why it's important to understand stuff and actually read the documentation and look at the formulas instead of just saying, why is this not working? I had the same learning rate as before. Now it's not working anymore. Now it's diverging. What's going on? Well, you have to understand what's actually how the terms interact. Okay, so I'm out of time. Next time, what I'll talk about is there's one more approach you can do. I wanted to get to it today, but you guys asked great questions. Which is, the other thing you could try to do is to try to be adaptive and try to see what's going on with the gradients. There's a way of doing it that kind of builds off of gradient descent momentum. And that's called the atom optimizer, which we'll talk about next time. And then we'll get into how you use all this stuff. Okay, lecture ends here. Switched office hours. Any questions?